Hello everyone, welcome to Toppscholars, the smart learning app. Today we are going to see the MHT-CET mock test series review for physics. Okay, so let's look at the next question now. Question number 11. The molar specific heat at constant pressure of an ideal gas is 7/2R. The ratio of specific heat at constant pressure to that at constant volume is what? Okay, so first of all over here, the molar specific heat at constant pressure is given to us and it is 7/2R. We have to find out the ratio of specific heat at constant pressure to that at constant volume. Okay, options are 9/7, 5/7, 8/7 and 7/5. Okay, so which of these is a correct answer? So it's a very simple question. First of all, the molar specific heat at constant pressure is given and it is Cp is equal to how much? 7/2R. Okay, now we know one thing, the Mayer's relation, it's a very famous relation. The Mayer's relation is Cp minus Cv is equal to capital R, the gas constant. Okay, now from here we can say Cv is equal to Cp minus R, isn't it? Cp minus R. So what we can do is we can put the value of Cp, which is over here. So 7/2R minus R is equal to 5/2R, isn't it? So now we have the value of Cv also. We already had the value of Cp over here, and now what we want is the ratio. So the ratio over here is going to be Cp upon Cv is equal to 7/5, isn't it? Cp over here is 7/2R, okay, and this is 5/2R. So 7/2R upon 5/2R, okay, definitely 1/2 R is going to cancel up and what will remain is 7/5 only. Okay, so this is going to be the ratio over here and therefore the correct answer is option D, that is 7/5. Okay, moving on to the next question now, question number 12. According to the Maxwell's law of equipartition of energy, the energy associated with a polyatomic gas molecule is what? So it is 3/2RT, 5/2RT, 6/2RT or 7/2RT, where R over here is the gas constant and T is the temperature, isn't it? So we have to find out what is the total energy associated with a polyatomic gas molecule, okay, or for example 1 mole of polyatomic gas. Okay, so the solution is very simple. Okay, according to the Maxwell's law of equipartition of energy, the mean energy associated with each degree of freedom of the molecule, okay, each degree of freedom of the molecule is how much? U is equal to 1/2 kBT, where Kb is nothing but the Boltzmann's constant, okay, and T is nothing but the temperature. So this is the energy associated with every degree of freedom of the given atom or maybe the molecule. Okay, so if you have, let's say, 1 degree of freedom, then this is the energy. If you have 2 degrees of freedom, then it will be twice. 3 degrees of freedom, thrice. N degrees of freedom, N times 1/2 kBT, isn't it? So this is the energy associated with a single molecule. But if you have, let's say, 2 molecules, okay, each having single degree of freedom, then total energy will be twice, isn't it? If you have 3 molecules, thrice. Okay, now if you have, let's say, 1 molecule or maybe 2 molecules, let's say, and let's say each one of those has got 2 degrees of freedom, then 2 times 2, isn't it, 4 1/2 kBT, isn't it? That will be the total energy, isn't it? Now since a polyatomic molecule has degrees of freedom equal to 6, isn't it? The degree of freedom for polyatomic gas molecule is how much? Nothing but 6. Okay, so therefore the total energy associated with 1 mole of polyatomic gas is 6/2 Na kBT. Why Na? Na is nothing but the Avogadro's number for 1 mole, isn't it? 1 mole is equal to how much? Exactly Na number of molecules or atoms. Okay, so therefore U is equal to this much, and we know NaKb is written as capital R, the gas constant, and therefore It is 6 by 2 RT. So the total energy associated with 1 mole of polyatomic gas is how much? 6 by 2 RT. So therefore, the correct answer is option C, 6 by 2 RT. Okay. So moving on to the next question now. Question number 13. For a perfectly black body, okay, for a perfectly black body, which of the following is true? Okay, first of all, few things are given. Small a is the coefficient of absorption, small r is the coefficient of reflection, and small t is the coefficient of transmission, isn't it? So, for a perfectly black body, which of the following is true? Options are a is equal to 1, r is 0, t is equal to 1. Then a is equal to 0, r is equal to 1, t is equal to 1. A is equal to 1, r is 0, t is 0. And then a is 0, r is 1, t is 0. So, which of these is true? So, the answer is very simple. For a perfectly black body, isn't it? All the incident light or radiation is always absorbed and nothing is transmitted or reflected back. We all know what is a black body. Black body is a body which has the property that whenever some radiation is incident on it, all the energy is absorbed by it, isn't it? It absorbs 100% of the incident radiations, isn't it? So therefore, definitely the coefficient of absorption is definitely equal to 1 and it does not reflect anything, isn't it? Or in fact, it does not even transmit anything. Okay, so therefore, the correct answer to this question is going to be equal to option C. A is equal to 1, R is 0 and T is also 0. Okay, so that's the answer to this question. Moving on to the next question now. Okay, question number 14. So over here we have a gas contained in a cylinder fitted with a frictionless piston. Okay, so it's a frictionless piston, that means there is no loss of energy. Okay, so we have a gas contained in a cylinder with frictionless piston expands against a constant external pressure. Okay, so over here the cylinder expands, okay, against what? The constant external pressure of 1 atmosphere from a volume of 5 liters to a volume of 10 liters. So initial volume and the final volume is given. So here there is an expansion going on and in this expansion the volume changes from 5 liters to 10 liters. In doing so, it absorbs 400 joule of thermal energy from the surroundings. Determine the change in the internal energy of the system. So we have to find out what is the change in the internal energy. Okay, so options are 10.6 joules, 106 joules, 1.06 joules or 1060 joules. So the solution to this is very simple. We all know, first of all, pressure is given, that is 1 atmosphere, and 1 atmosphere we have to convert it to SI units, right? Atmosphere, ATM is not definitely the SI unit, so we have to convert to pascals. 1 ATM or 1 atmosphere is 1.013 into 10 raised to 5 pascals. Okay, moving on. Initial volume is 5 liters, so we have to convert to meters cube. So 1 liter is 10 raised to minus 3 meters cube. So therefore, 5 liter is 5 into 10 raised to minus 3 meter cube. Similarly, the final volume is 10 liters and therefore it is going to be 10 into 10 raised to minus 3 meter cube, isn't it? Now, the change in volume can be calculated over here. 10 minus 5 is definitely 5 into 10 raised to minus 3 meter cube. So that's the change in volume. Now, heat absorbed over here is how much? 400 joule, isn't it? Heat absorbed is how much? 400 joule. Okay. Now, we know the total work done is what? Total work done is equal to always W is equal to P into dV, that is pressure into nothing but the change in volume. So pressure is already known to us, that is given over here. Change in volume is also given over here. So after calculating, this is the work done, isn't it? Okay. Now the thing is, we have to determine the change in internal energy of the system. Okay. So according to the first law of thermodynamics, we know delta Q is equal to W plus delta U. That means the heat that has been given to the system or heat that has been lost by the system, okay, that is equal to work done plus the change in internal energy. So therefore, change in internal energy is nothing but delta Q minus W. Okay, so we have this simple formula with us now. Delta U over here is going to be equal to 400 minus 506, isn't it? Delta U is 400 minus 506 because we know delta Q, okay, that is heat added is 400 joules, and we have just found out the work done, and that is 506 joules. So after calculating, we get minus 106 joules. So change in internal energy is how much? Nothing but minus 106 joules. So therefore, the correct answer is minus 106 joules. Now here there is a negative sign, and this negative sign indicates that the internal energy has actually decreased. Okay, so this indicates decreased internal energy, okay, during the process. So correct answer is option B, 106 joules. Okay, moving on to the next question, question number 15. Okay, here is an interesting question. A pendulum clock consists of iron rod connected to a small heavy bob. Okay, so we have a pendulum clock consists of iron rod connected to a small heavy bob. If it is designed to keep correct time at 20 degrees Celsius. Okay, so it is designed in a way that it will keep the time correctly at 20 degrees Celsius. We all know one thing, whenever the temperature changes for any material, then it starts expanding or contracting. If the temperature increases, definitely it will expand. If the temperature decreases, it will contract. Generally, that is what happens. So it has been designed for working at exactly 20 degrees Celsius, isn't it? Now, how fast or slow will it go in 24 hours, okay, at 40 degrees Celsius? That means if the temperature changes to 40 degrees Celsius, then what will happen? Whether it will slow down, okay, or it will become faster, okay, that is what we have to find out over here. Okay, so temperatures are given, initial temperature and final temperature, and after 24 hours, okay, what will be the change? That means if the temperature is now 40 degree, then after 24 hours, what will be the decrease or increase in the time interval in that clock? Okay, that is what we have to find out. Over here, coefficient of linear expansion of iron is given, that is 1.2 into 10 raised to minus 5 per degree Celsius. Okay, let's look at the options. 5.2 seconds, 10.4 seconds, 1.2 seconds, or 7.6 seconds. Okay, so let's look at the solution. It's very interesting. Okay, so first of all, we know one thing, the time period of a simple pendulum is given as T is equal to 2 pi under root capital L upon G, isn't it? Capital T is equal to 2 pi under root L upon G. Okay, that's the standard formula for a simple pendulum and its time period. Okay, now the thing is, at temperature theta, okay, let L, the length of the rod, is L theta, because we know the length of the rod depends on the temperature, because as we know, if the temperature increases, definitely its length will also increase, isn't it? So therefore, let's say at temperature theta, the length is L theta. Okay, now therefore we can say T is equal to 2 pi under root L theta upon G. But we know one thing, L theta is equal to L naught in brackets 1 plus alpha into theta, isn't it? 1 plus alpha into theta, where alpha over here is the coefficient of linear expansion, isn't it? Alpha is what? Coefficient of linear expansion. So L theta is equal to L naught, okay, into 1 plus alpha theta. L naught is nothing but the length at 0 degree Celsius, or we can say initial temperature. Okay, so therefore T is equal to 2 pi under root L naught 1 plus alpha theta. We have just put the value of L theta in this equation, okay, and we got this. Now after solving this, what we get is, see here, okay, we can take out this term from the roots, and therefore it will be 1 plus alpha theta raised to 1 half. Okay, so T is equal to 2 pi under root, okay, under root L naught upon G, and out of the roots we have 1 plus alpha theta raised to 1 half. Okay, this power raised to 1 half is nothing but under roots only. Okay, so over here we have just found out this very simple equation, very interesting equation. T, the time period of a simple pendulum, okay, with a rod is 2 pi under root L naught upon G, and here we have 1 plus alpha theta raised to 1 half. Okay, now over here this term, if you see, this is nothing but T naught, because we have L naught, the initial length. So this is T naught, isn't it? So therefore we have got a formula, what? T is equal to T naught 1 plus alpha theta raised to 1 half, isn't it? So therefore we can say T is equal to T naught 1 plus 1 half alpha theta. What we have used is, we have used the binomial theorem and we have used the series expansion. So 1 half will come in here, okay. So T is equal to T naught 1 plus 1 half alpha theta, okay. Thus we can say T, the time period at 20 degrees Celsius, is equal to T naught 1 plus 1 half alpha 20 degrees Celsius. We have put the temperature, and therefore it is going to be equal to T naught 1 plus alpha 10 degrees Celsius, because there is this 2 and this 20, they are going to cancel up. So finally we get T naught 1 plus alpha 10 degrees Celsius. Similarly, we can write for T40, the time period at 40 degrees Celsius, it is going to be equal to T naught 1 plus 1 half alpha. Now theta is 40 degrees Celsius. So this 2 and this 40, they will cancel and we get 20 only. T naught 1 plus alpha 20 degrees Celsius. And now if we divide these two, what we will get is this. See, we have divided this equation and this equation, and we have got this equation, isn't it? Okay, so after dividing, finally what we get is this. What we have done is, the term which was in the denominator has been taken to the numerator. Therefore you see here the inverse sign, okay. And now again, if you use over here the binomial theorem, then it is going to be minus 1 over here. So this 1 plus, which was already there, now we have 1 minus alpha, because we have just expanded these powers, okay. So finally after solving this, what we get is this 1 plus alpha 10 degrees Celsius. If you just multiply these terms, you will get this only, 1 plus alpha 10 degrees Celsius, okay. So if you take this 1 to the other side, you get T40 upon T20 minus 1 is equal to alpha 10 degrees Celsius. And if you just cross multiply over here, okay, what you get is this, here it is, T40 minus T20 upon T20, we have just cross multiplied over here. So what we get is this. So now we know these numbers, alpha is here already, okay, and this is 10 degrees Celsius. So therefore what we get is this finally, okay, T40 minus T20 upon T20 is 1.2 into 10 raised to minus 4, isn't it? Now moving on, this is fractional loss of time, isn't it? This is the fractional loss of time. As the temperature increases, the time period also increases, isn't it? Why it increases? Because when the temperature increases, the rod, okay, expands linearly. That means its length increases a little bit, and we know time period depends on length, isn't it? So therefore, as the length increases, time period also increases. And what is time period? Time required for one complete oscillation, okay. So over here, the time for one oscillation will increase, isn't it? That means the pendulum will become much slower, and therefore the clock will also become slower, isn't it? So thus the clock goes slow, isn't it? The time period has increased and therefore the clock has gone slower, okay. Now this is the fractional loss, isn't it? This is the fractional loss, okay, small fraction that is lost. So the time lost in 24 hours is delta t is equal to this fractional loss into 24 hours. So therefore, we get what we get is we have to convert this 24 hours to seconds. How we will convert that? It's very simple. Here it is 1.2 into 10 raised to minus 4 into 24 hours. That means how many minutes? 60 minutes, and each minute consists of 60 seconds. So after we solve all these things, finally what we get is 10.4 seconds. So the correct answer over here is 10.4. So the answer is going to be option B, that is 10.4 seconds. So this is the loss in time, isn't it? 10.4 seconds, because your clock has gone slower. That's why this is going to be the loss in time.